So what we are doing with this little finish-up unit is some theorems based on proportionality in triangles. So let's see what we got here. So I'm looking at this picture. A triangle has a segment in its interior, and it's parallel to one side. So it's parallel to one side, forms a similar triangle inside the original. Because of angle, I'm making that big statement here. So I'm basically looking at this triangle JKN, and I'm looking at the bigger triangle JLM. And I'm saying angle. So I'm first starting with angle J being congruent to angle J. So why is angle J congruent to angle J? Amanda, how come?
Because of the reflexive theorem of angle congruence.
Over the reflexive theorem of angle congruence. So angle J will be congruent to itself. Now I'm also stating that JKN is congruent to JLM. Why is JKM congruent to JLM? A little hint here, subtle hint. Jack, how come? Corresponding angles of parallel lines are congruent. Remember, the parallel line part is important. They're not necessarily congruent unless these lines are parallel. So I've got angle. I could have, not even done the reflexive one. I could have said, well, I've got corresponding angles here. So you could have said angle because of these two or these two. Doesn't really matter as long as you can find two of the corresponding angles. Just as a little reminder, a mid-segment is kind of a special case here. But I don't know necessarily that this is a mid-segment. I only know that they're parallel. But mid-segments are parallel, and you get the congruent on both sides. Parallel lines and segments will create similarity in other places because of these angular properties. So we're going to look at different cases of having parallel lines in different spots. So this leads us to the triangle proportionality theorem and its converse, because this is an if and only if. It's a bidirectional, biconditional statement. A line is parallel to one side of a triangle if and only if it intersects the other two sides proportionally. Meaning that if you want these two things, well, these two things are parallel means that RT to TQ equals RU to R to US. Or you can also say if RT and TQ are proportional to RU and US, you have parallel lines. So they go back and forth that way. So it's maybe a little hard to see what this is trying to say. When these things are parallel, this to this, RT to TQ, is the same as RU to SU, or US. So let's just kind of look here. So if you're given a triangle like this one, and this is an example on your paper there, find RQ. I want to find this thing. Set up a proportion. Well, this states this piece to that piece equals this piece to that piece. RQ to QU, RQ to QU equals RS to ST. This piece to this piece, that piece to that. How do I know that? Because I've got parallel lines here. Only can do that if I know they're parallel. So now let me put the numbers in, or what I know or don't know. I don't know RQ, but I know QU. I know RS, and I know ST. Cross product. So 6x equals 36. So whoops, x is 6. So that piece to that piece, that piece to that piece. Yes, sir. Yes, sir. How'd you do it? Okay, so how'd you do it? Speak really loud, I can't hear you. Well, what? That's not a triangle. The 9 over 6. Okay, so you went Q. All right, let me see what you did. You did QU to ST equals what? This one to that one? Well, scale factor is a division, right? This is a division. I'm just trying to show why you're probably okay with what you did. Because look at this, the cross product. RQ times ST. RQ times ST is QU times RS. So you said, I went this to this equals that times that. That to that, rather. You did 9 over 6, right? That's how you got a division or whatever you got there. Equals x over 4? Huh? Yes, but isn't it exactly what you did, though?
Yeah.
So you basically, you just kind of turned the proportion around, and that's okay. Just make sure they're equivalent to our theorem. Alrighty, we got another theorem here. If three parallel lines intersect two transversals, so it's all sideways here. Here are my parallel lines. They're kind of up and down. And here's my two transversals. Then they divide the transversals proportionally. So UW, UW to WY is the same as VX over XZ. This to this equals that to that. So let's look at an example here. I want to find the X value. Now I'm seeing all these little right angles, and these are corresponding angles that are congruent. So if corresponding angles are congruent, what can I conclude about these three lines? Amanda?
They're parallel.
Right? Because that was the Converse theorem. If corresponding angles are congruent, then the lines are parallel. Well, now I'm in this situation. So this piece to that piece, this to this, x over 51 is going to be the same as that to that. 36 over 54. So 54x equals 36 times 51. I multiplied this out. So 54x equals, I got 1,836. Anybody else getting that? Divide both sides by 54. What are you getting? 34? So here's this piece. So if they're parallel, this to this equals that times that. You could go this to this equals that to that, because that is just another way of saying this, but I'm switching the names, I guess. So just make sure you have equivalent proportions if you're looking at it differently. You can say UW is to VX and WY is to XZ. This to this is that to that, because their cross products will be the same, switching the meanings. With me so far. One more theorem, and that's it. I'm pretty sure that's my last theorem coming up here. Okay, if a segment is an angle bisector, now how do I know this is an angle bisector? Because they're showing me that these two angles are congruent, so it's bisecting that angle. Then it divides the opposite side, these two sides, other side, into segments whose lengths are proportional to the other two sides. What? All right, let's see what this is saying. AD is to DB. So this one is to this one, as AC is to BC. This to this is that to that. Now for some reason, I have a little mental block with this one. I always remember this is to that, as that is to that. So does that work? Can I say CA is to AD, as CB is to DB? I always remember it this way for some reason. And is that okay? Are these equivalent? These two proportions equivalent? How would I know if they're equivalent? How can I tell? True or false? If this, then that. How can you tell? Cross product. What's the cross product here? AD times CB equals DB times CA. What's the cross product here? AD times CB equals DB times CA. Because I don't know why I remember it better this way, but I just do. So I'm just saying that because sometimes I will solve these that way. So that's like the theorem. And you're right, it is. But it's this to this, is that to that. So now you have to kind of recognize when you have that situation. So the example on the bottom of the page, first of all, it's showing that these two are congruent. So what is this piece? If these two are congruent angles, what do we call this thing? Amy? An angle bisector. So I have an angle bisector. So this to this is this piece to that piece. This to this piece to that piece. The only problem is, what's this piece? I know the whole thing's 28. I know this is x. So what's this piece? If this piece was, say, x was 10, how would you find what this piece is? What? Yeah, you'd say it's 18. You subtract that out. So this little piece is 28 minus x. So 8 is to 24 as 28 minus x is to x. So let's see, I've got 8 times x equals 24. Don't forget your parentheses. And do a little division here. I'm going to divide both sides by 8. So I'm getting x equals whatever 3 times 28 is. That was this 21. 81? No. 24. So 84, tell me, you've got calculators, I don't. Okay. Okay, so then I'm going to add that 4x equals 84. And then I'm going to get x is, I want to say 21? Is that right? And that's what they want this time. Okay. This piece to that piece and that piece to that piece. So if you don't have that many things to remember now, what do we just do? If you have a situation where there's parallel lines, this to this is that to that. If you have several parallel lines with transversals, this piece to that piece equals that piece to that piece. If you have an angle bisector in a triangle, this to this equals that to that. Was there a question? Yes. Dividing what? Well, yeah, because think about it. You know, if it's, you don't divide both things because that's 2 divisions. Right? You're just going to divide either this factor or that factor. Easier for me to divide that factor. So it's basic. I mean, that's it. The rest of these are can you apply them? So I want you to take a few minutes, and on the back it's all just practice and work on them. So take a few minutes, and then we'll kind of review. So let me put up the answers for what I got for these. The first one is saying yes, because I compared 16 over 18 with 24 over 17. A couple ways you can do this. I think the easiest, especially if you have a calculator, is just look at the cross product. And so I got that they were equal. So kind of looking at the converse of that theorem, if those are true proportions, then they must be parallel. Yes? You can. But you have to kind of show that you've got equivalence here. For part B, so for part B, I see that these are parallel. So this to this has to equal 6 to an unknown. I did 4x equals 60, so this is going to be 15. This one, let's see, find the E. Now, they're not telling me they are parallel. Not directly, anyway. How are they telling me that they're parallel? Well, what's going on here with this? So if I'm just looking at A, D, and BE, what kind of angles are these? What are they called? Alternate interior angles. Are they congruent? Or is that one way? Yes, right? So what can I conclude? These are parallel. I've got the same thing over here. This one is congruent to that one. Alternate interior angles are congruent, so the lines are parallel. So you kind of have to do that first. To say, okay, I do have parallel lines. That means I can set up the proportion. This to this equals that to that. DE is the I don't know. So 21 over 28 equals x over 30. Oops, equals x over 32. Solve that however you like for x. I think I took cross products, and I got this equals that, and x came out to 24. Yes? We proved it. We proved the cross product by using the multiplication property of equality and the division property of equality. Yes, it's a cross product property. Cross product property which we proved. Okay, so and then this one, let's see, this to that is that to that. I know that because this is an angle bisector. So I don't really know what this piece is, so it's 33 minus x. What am I trying to find? I'm just trying to find AV. So 45 is the 54, as x is to 33 minus x. Take cross products, you should get AV is 15. Did I do this the same way you did it? Are there questions on these 4? We're going to let you finish them. Let's see what's going on here. Determine whether these are parallel, MO and LP. Well, how can I determine they're parallel? We've got that theorem that says if this over that equals that over that, then the lines are parallel. So basically asking, is 12 over 10 the same as 18 over 16? Question mark. So go this way, go this way. Do you get the same number? You don't, right? This cross product is not equal. I'll let you kind of fill in those details. So, therefore, the lines are not parallel. If they were equal, I would say they were. So those did not work out. What have we got here? A farmer's land, okay, divided by this newly constructed interstate. So it's showing the distances in meters. Find the distance CA between the north border and the south border. So they want you to find this whole thing. They're showing you these are parallel roads here, the north border, the south border, and the interstate. So actually, I'm going to make this be x. So this piece here is x minus 2,000. Because this is what I want to find, right? That's why I'm making that x. So this to this equals that to that. 2,000 over x minus 2,000 should equal 2,500 over 3,000. Is that the correct proportion? I think so. Now if you do all this magic, I guess I should put the answers up here. You should get 4,400 meters. Yes?
In the U.S., isn't it illegal to put an interstate through someone's land?
I have absolutely no idea.
Maybe
Yes.
it's like an anarchy country. Like if there's something
Yeah, Joseph? What'd you do? You could do, remember, these are equivalent. You can go this to this is that to that, or this to this equals that to that. They are equivalent on proportions. So you can do it either way.
Now, instead of making ACS, I mean BCS.
You can absolutely do that. Make this x, and then you added them, right?
Yeah.
Yep, that's perfectly fine. Just remember what you're looking for. You want that whole distance. Absolutely fine. Question?
I can't get the right answer on D.
On D?
Yeah, like D. Like find D, you know? And D always turns out to not be 15. I mean, I was on my logic that it's 15, but then when I do the equation, the cross
Let me see. I can divide by 9 here just to make this a little easier. I don't have a calculator. It's 5 times 33. Help me out here real quick.
165.
What?
165.
165?
Yes.
Wait a second, how did it get that?
I divided by 9?
Wait, well, how are you able to divide by 9? I mean,
Division property of equality.
it says like, I don't know.
165 divided by 11
over
is
45
15.
equals 33 minus x
So
over
it's just
54. So it has to be 45 times 33 minus x equals 54x.
Do I get it? I don't have a calculator. what's 165 divided by 11? Somebody help me out here.
I really don't understand how this works.
Now let's look at these last two. I say that they were not parallel. Now they don't look parallel, but that's not good enough. Maybe it is, it's just a bad drawing. So I said, well, let's see. Does that over that equal that over that? And it did not. So since they didn't equal each other, this one not parallel to that one. And then this guy here, okay, what was going on here? Idaho Avenue bisects. That's all I needed to hear. This is an angle bisected, this piece right here. I'm kind of drawing those streets so I can see them a little bit better. So to the nearest yard, what's the distance along University Avenue from 12 to Washington? I think they want this distance, right? So that means this to this equals that to that. So x to 700 yards equals 200 to 400 yards. And I did do all that, and I think I got 250 because this is actually a 1/2. So when I saw that that was 1/2, it made it a little bit easier. 2x is 700, so x is 350 yards. Yes, sir. Yes. You give me the units. Jack.
Those are really big dots.
Those really big dots?
The for number for letter A.
What dots?
Proportionate to the streets, they're really big dots.
Okay. Well, what would I say? All right, so these are those 3 theorems. So I'm going to give you a homework paper, but before I do that, I actually have a little checkpoint. So I want to make sure we're all good with these similar triangles. I will give them back to you next class during our review, so that if you have any remaining questions, we can get those taken care of.